quantum phenomena did not exist before the humans appeared on the planet. It's the same old thing. Does sound exist because we hear it, or is it, for example, if a tree falls? That's the next one, please. So Heisenberg had a different view. He was one of the founders of quantum physics, or the new quantum physics. Of course, Einstein was the founder of quantum physics anyway, and with Planck. The laws of nature which we formulate in quantum theory deal no longer with the particles themselves, but with our knowledge of the particle. So it's a theory, it becomes a theory of knowledge. So it becomes applied epistemology. The conception of objective reality evaporated into mathematics that no longer represents the behavior of elementary particles, but our knowledge of it. This is Heisenberg's position. So to him that what he's doing is reality, dealing with reality. He's not worried about if there exists an objective reality without our theory and without our experiments. Next one, please. Pascal Jordan, who is practically forgotten today, except in mathematics, they still study Jordan algebras and all that. He was, you see, a lot of people don't know that even in algebra, Emmy Noether was a very important physicist, theoretical physicist. At that time. Okay. Observations not only disturb what has to be measured, they produce it. We ourselves produce results of the measurement. See, that's extraordinary. And this is like saying that a doctor causes the symptoms and the disease with his test. Okay. So disease doesn't exist without the doctor. Okay. So there is no such thing as a patient. Okay. Jordan was a tragic figure. He became a Nazi stormtrooper and then threatened Max Born, one of the founders of quantum physics, and he was the head of physics at Göttingen, which was the birthplace of quantum physics, pretty much, and several people had to leave. Okay, next one, please. Next to Einstein, Niels Bohr was the most important physicist of the 20th century. So he said it's wrong to think that the task of physics is to find out how nature is. Okay, he says physics concerns what we say about nature. That means our pronouncements are what are subject to test. So it brings it close to some sort of a prophetic religion. So the words of the prophet are the religion. There is it has no connection with nature or reality. That's what he said. Before one talks of reality, one must specify the experimental arrangement one is going to employ. Even Feynman doesn't put too much on this. You know, Feynman is very his 3-volume book, the 3rd volume is on quantum physics, is very much experimentally oriented. It's not a mathematical book, it's a physical book, physics book. Okay. That is, there is no reality without the observer. This is the central problem of physics. What are we, actually when we talk about quantum theory, what is it a theory of? Yeah?
So, but physics, I mean, as far as I read it, physics does, like, in case you can come up with a theory which says there is reality, physics is okay with that. I mean, if you can explain everything satisfactorily, then physics is totally happy with that.
Nobody has explained it satisfactorily.
That's true. But like at least conceptually, if somebody came up with like a very coherent
theory,
physics would be happy to do.
Or we'll be most happy. But nobody has come up to it so far. Quantum physics doesn't do that. That's the problem. As it exists today, quantum theory doesn't do that. Yeah.
When you say there is no reality without...
I didn't say that. They are saying.
No.
Yeah.
No, but it is with respect to the observer and not with respect to non-observer.
Yeah, but what they are saying is there is no objective reality. That means Einstein's position is there is such a thing, but you haven't found it. Your theory doesn't, for example, with relativity theory, there is no problem. E equals mc squared, that formula is true. Regardless of, you can't say the formula is true because of the atom bomb.
No, E equals mc squared is true for the person who knows that equation.
No.
For the person who doesn't know that equation,
that is true regardless, because otherwise sun would not be shining.
Yeah.
Whether you know it or not.
So
the thing is, it is not dependent on any experiment. Yeah. It's not dependent on the experimental observer.
True.
Yeah, but the point is problem with quantum physics, it's not like that. That is the problem. We'll get to that. When you look at the wave equation, there is no wave. There is no wave that's independent. Yeah, next one.
I'll ask you.
Yeah. You see this one. This gives us two worlds. The physical world, which is objective, which is what Einstein and others would like to have, and then the world of the physicist, which is the observer and the apparatus. But what Bohr, Heisenberg, and all these people are saying is that doesn't exist. So our physics is only about this, and this is not physics. It's evaporated into mathematics.
Did they actually say it doesn't exist, or did they just say it's not their job to explain?
Both.
So they actually did not.
You say, no, the thing is, there is no such thing. They say there is no such thing as objective reality. That's what Heisenberg says. It evaporated into mathematics.
So that is his personal philosophy.
But that's his personal philosophy. You know, but you see, in classical physics, there is no room for personal philosophy. You see, for example, Ernst Mach refused to believe in atoms because he said they cannot be observed. But then later that was demolished by the Brownian motion and all that kind of thing. Yeah, next one, please. So, in classical physics, including relativity, there is no problem with reality. You see, we use the term classical physics now to include relativity also. And then quantum physics began with waves from particle duality. Found that basic laws of physics are violated in the quantum world. One, the most basic of all, is the limit imposed by the speed of light. That is violated, and a lot of people, we don't teach that. We don't tell them that, because we don't go into details of that. But I want to design a course of modern physics that can be taught with the help of experimental descriptions to high school students without going into too much mathematics. Okay? Even basic concepts like position, velocity make little sense in the quantum world. We'll get to that. Okay? So relativity is concerned with the macro world where gravity is a major force. So velocity of light sets a limit on speed. Both conditions are violated in the quantum world. Gravity plays no role at the quantum level. What happens if there is no gravity? What is due to in the general relativity? What is gravity due to? It is due to the presence of mass. I mean, even in classical physics. But then, even in Newtonian physics, it is the attraction between masses. But then, relativity, the great problem Einstein had with Newton's gravity, Newtonian gravity, was the fact that it requires action at a distance. What happens? How does the sun know the position of the planet Earth when the velocity of light is the limit? It takes 8.5 minutes for light to travel from the sun to Earth, and then from Earth to sun, so total 16 minutes. And the Earth itself is moving. But the gravity is always, you see, which means the gravity is changing. The attractive force is changing. How does it know? That's a problem, because it takes, by the time the sun receives the message about the position of the Earth, the position of the Earth has changed, because it's traveling at about 30 kilometers per second. And therefore, in 8 minutes, it has traveled quite long. So how does it know the Earth is not here, it is somewhere here? So the force should be exerted there. How does the sun know? So for that, Einstein came up with the idea of 4 field equations. So first, of course, he had to come up with the principle of equivalence, that gravitational mass is the same as the inertial mass. The inertial mass is, you can think of, I mean, even mass has a dual part role. One, of course, it is the cause of gravitation. Second, the inertial mass, one way of looking at it, which makes sense here, is to look at it as concentrated energy. Mass is energy by Einstein's relativity. It's also what needs to be overcome in order to move it. That is what we call force or energy. Okay. But the Einstein's thing was that gravity causes curvature in space-time. So field equations, therefore it changes the geometry of space-time. That is Einstein's general theory of relativity. So it's not any force of attraction because, for example, if you have space like this, and then you see, so there is curvature caused by the presence of mass, and therefore our bodies are attracted to it because of the curvature. That is essentially an oversimplification of Einstein's field equations of general relativity. Then you don't have any problem. As long as there is the mass is there, the field equations are there. So the space becomes curved because of the presence of all these masses, and therefore there is no action at a distance. It is due to curvature itself. So the velocity of light doesn't present a problem. The limit doesn't present a problem. Okay. Gravity plays no known role in quantum world. So, for example, I brought this up when I was at CERN. They were talking about, the Big Bang experiments they're doing. What they're doing is really particle physics experiments, and essentially, you see, let us understand one nice thing about. If you have any problems with some of the technical things, please ask me the question. So we'll keep it informal, because we have a small thing. What essentially a Big Bang is the reversal of a black hole. Black hole absorbs everything, light and energy, into a small body. But Big Bang says you start with a small body, which is already a black hole, and then you expand. And the theory is that the particles that come out, the belief is that the particles which have to come out of it during the Big Bang can be observed in that experiment, in the CERN experiment. More particularly, they have to look at this thing, what you call it, the Higgs boson. That's what they're looking for. We don't have to know what all it means. So I asked them the question, you are not able to simulate gravitation. How are you going to simulate, how do you say that you're looking for some particular particle under some conditions?
Supposed to be very weak, right, at those scales. Gravity, yeah.
Gravity, the order of magnitude is so small.
Yeah,
so the thing is, you might as well assume it is zero. That's what I'm going to do now. But the point is, then how can you say, but the thing is, gravity is the dominant force in the Big Bang. Because there is no black hole. Black hole is an offshoot of the general relativity, which is a theory of gravitation. So, if you cannot simulate gravity, how can you say you are simulating a Big Bang? So finally it came out. It's a very expensive experiment. If you say you need $15 billion, I work with NASA programs and all that. I know how to justify large budgets. So if you say you are going to, you need $15 billion to look for the Higgs boson, nobody is going to give you that kind of money. No government is going to do that. So they had to come up with a more sexy title. We are going to simulate the Big Bang, the creation of the universe and all that. It's really a very important experiment and of particle physics. But so far, the particle we are looking for, that is so-called God particle, the Higgs boson, has not been found. Okay? So a locality is a region in which the velocity of light sets the limit. Okay, next one, please. Quantum is, we can think of it as atom of radiation. Okay, just as atom is the smallest, no longer, but assume it is the smallest. It's atomic theory. So quantum theory also is atomic theory, part of atomic theory. And so Planck introduced the quantum of action as a mathematical device to explain emission and absorption of radiation.